Welcome back. This week, we are going to review probability theory. All of you should have taken a course in probability theory prior to this class, so you should have taken 202 or the equivalent, which devotes a whole quarter to the study of probability theory. The reason that we do a review of it here is because I think it's a very difficult subject. I will tell you that it didn't stick the first time I saw it. It's a little bit like Calc 2 also didn't completely stick the first time I saw it. I had to really see it a second time before a lot of those ideas made sense. So we're going to spend a week reviewing the big ideas from probability theory. The reason we're doing this is we're going to need it for the upcoming chapters. So topic we're going to do in 2 weeks is estimation, and so we need kind of the basic tools of probability theory in order to do maximum likelihood estimation, method of moments estimation, so we need it for that chapter. We also need it to do confidence intervals and hypothesis tests. So oftentimes, hypothesis testing gets taught without really grounding it in the math and the probability theory. But if we understand a few of these main results, then when we get to hypothesis testing, it's not just a matter of memorizing formulas. You'll be able to understand where those formulas come from and why they work. All right, so let's jump into probability theory. What we're going to focus on is the random variable. So what is a random variable? Well, quite simply, random variables are functions. So they're functions from the space of outcomes that can occur from some random experiment to the set of real numbers. So let me give you a concrete example of this. This is an almost trivial example, but the way I kind of understand things best is if I start with the simplest non-trivial example, and if I really understand a non-trivial example, then when I take it to a more complicated setting, if I understand what's happening in the simple setting, I can also understand what's happening in the more complicated setting. So I'm going to go over to the document camera, and let's say that I take out a dime and I take out a quarter from my pocket. So I have a dime and I have a quarter. And what I do is I shake these two coins up in my hand, I throw them up in the air, and they land on the table. All right, so that is my random experiment. Remember, a random experiment is some well-defined procedure that has an uncertain outcome. So I really don't know what's going to happen when I throw this dime and quarter up. So more precisely, when they land. So what could possibly happen? Well, what could happen is my sample space. So one possibility is the dime comes up tails, and the quarter also comes up tails. So that is one outcome. But it's not the only outcome. Another possibility is the dime comes up tails and the quarter comes up heads. Another possibility is heads, tails, and heads, heads. Those are the only 4 possible outcomes from this random experiment. But this is not a random variable. So remember what a random variable is. It's a function that maps from the space of outcomes to some set of real numbers. So here is a random variable. Let's say that x is equal to the number of heads that I get when I throw these 2 coins up in the air and watch them come down. I think I'm going to make my screen just slightly bigger. Maybe that's a little bit easier to read that way. All right, so I am now going to tally up my x values, and so this is my function. So this outcome maps to the x value 0. this outcome maps to a 1, this outcome maps to a 1, this outcome maps to a 2. All right, now, what we usually do with this is we summarize the this random variable with a probability mass function. So probability mass function just tells us the probabilities that we're going to observe each of these values of x. All right. So let us further assume that these are two fair coins and that they're independent of one another. So the outcome from the dime does not affect the quarter or anything like that. If that's the case, each of these outcomes will be equally likely. So each of these outcomes will have the same probability. So in that case, I'm going to go make another table and just summarize the possible values of x. So x can equal the value, the way we write this. So big letters are usually random variables. Small letters are specific instances of that random variable. So the probability that my random variable x is equal to a little x of 0, it would be 1/4. So 1/4. Why? Because there's only one of these four outcomes that is a 0. The probability that x is equal to 1 is a half, and then the probability that x is equal to 2 is also 1/4. Now, what I like to do whenever I make one of these tables is to have my last row be the sum. So the sum of these has to equal 1. If this doesn't equal 1, you made a mistake and you need to go fix it. All right, so that is a PMF. This is a PMF, which is a probability mass function that tells us the value of each individual x. By the way, we can go graph the PMF. So x, this would be the probability of x, would look something like this. So this is a quarter, this is a half, and so I would have a bar that looks like this, and there is my PMF. Notice the area under this curve is equal to 1. Corresponding to the value down here. So something has to happen if my random variable is well defined. That's a 2, and this is my x-axis. All right, let's go back to the course packet for a second. In this table, I've summarized all the main results that you may care about with random variables. So first thing is we have a probability mass function. Probability mass function is just, in the case of a discrete random variable, just gives us the probability that that value occurs. In the case of a continuous random variable, remember we don't interpret the probability density function as probabilities. The way we get probabilities is the same way we got probabilities with a histogram, that is with area. So the probability that some PDF is between A and B is just the area under the curve between those values. All right, the next thing that we had was a cumulative distribution function. So let's just go work out the CDF for my little toy problem here. The way we can write this is the probability that some random variable x is less than or equal to some little x value. So the CDF here is going to be 1/4, 3/4, and 1. Now we could do the exact same things that we were doing with our frequency distributions last week, and I could ask you questions like, what's the probability that x is, say, greater than or equal to 1? What's the chance I get 1 or more heads? Well, the way we were doing this last week was to write this as 1 minus the probability that x is strictly less than 1. In other words, x is equal to 0. Which would be 1 minus 1/4 equal to 3/4. Or you could just go add up those two numbers in this case. But in general, we want to get in the habit of using the CDF function rather than just summing the PDF, or PMF in this case. All right. The next thing that you probably did back in probability theory was to compute the mean or expected value. And so the definition of the expected value in the case of a discrete random variable is we're just going to compute the sum of x times the PMF. In the case of a continuous random variable, it's the integral of x times the PDF. All right, so let's go see this in action over here. So remember what our mean is. You know, think of it as how many heads do you expect to occur? So if you throw the dime up and the quarter up, how many heads do you expect? So I'm going to make myself a new column here. It's x times the probability of x. And so this is going to be 0 times 1/4, which is 0. If you allow me, well, this is 1 times 1/2, which is equal to 1/2. This is going to be 2 times 1/4, which is equal to 1/2. Therefore, the mean of x is equal to 1. All right, so what that tells me is I expect 1 head. Sometimes I get fewer than 1 head. Sometimes I get more than 1 head, but on the average I get 1 head. Another interpretation that we had last week is if I stick a wedge at the value 1, so there's my mean, the mean of x. This histogram or probability distribution would be in balance. So that's the middle of the histogram. All right, so that's means. We also you also would have learned how to find the expectation of some function of a random variable. So let's go see how that works. I'm going to define myself another random variable. So let's say that this is some sort of a gambling game. And so y is the payout. And suppose that somebody said, I'm going to give you $10 for every head that comes up. Then this would be 10 times x. So we can think about having a new random variable y, and y then takes value. If 0 heads comes up, I get $0. If 1 head comes up, I get $10. If 2 heads come up, I get $20. And we could ask ourselves, well, what's the mean of y? So how much money do you expect to get? Well, one thing that's really important to notice is that the probabilities of 0, 10, and 20 are exactly the same probabilities as having 0, 1, or 2 heads. So the expected value of y is going to be just this, y times the probability of y. So this is going to be 0 times 1/4, which is still 0. This is going to be $10 times 1/2, which is equal to $5. And this is going to be $20 times 1/4, which is $5. Therefore, the mean of y is $10. So I expect a payment of $10. Now, if we go back to my table here, there's an extremely important formula that you should know by heart. It's one of the most important formulas, which is we can find the expectation of a linear combination of a random variable just by, well, let me write it out here. So the expectation of y is equal to, well, the expectation of 10x, you can think of plus 0. Now what that formula says is we can pull out all these constants. This is equal to 10 times the expected value of x plus the constant, which is 0. All right, so let's go work this out. This is 10, but the expectation of x is 1. That's mu sub x. and we can just forget the 0. Therefore, the expected value of y is $10, and that's exactly what I did when I did it the hard way. So we can think about this is the hard way, this is the easy way. All right, let's go back to my summary of what we do with random variables. So the next thing that you would have learned in probability theory is what's the variance. So you can think about the variance as the expected squared deviation from the mean. So what's the typical squared deviation from the center of the distribution? How far do I expect to be from the middle in squared units? That's what the variance is. All right, well, let's go find the expected squared deviation from the middle. So I'm going to come over and we're going to add a column here. And so let's find the, well, I'm going to write it like this. Let's start out with x minus mu squared. Actually, let's just go all the way. We're going to multiply this times the probability of x. All right, so this is going to be 0 minus 1. Okay, so if I get 0 heads, I'm 1 away from the middle, squared. And then how much weight should I give that? Well, that only comes up a quarter of the time, so we're going to multiply by a quarter. So 0 minus 1 squared is 1 times a quarter, so this is a quarter. Well, let's move on. We're going to have 1 minus 1 squared. So if I get 1 head, how far is that from the middle? Well, it's 0 from the middle. How often does that occur? Well, half of the time. So maybe I should put a little dot here indicating that we're going to multiply that. So this is obviously 0. So 0 times a half is 0. Well, let's go finish this off. If I were to get 2 heads, I am 1 away from the middle. How often does that occur? Well, it occurs about a quarter of the time. And therefore, this is going to be 1 squared times 1/4, which is a fourth. Therefore, the variance of x, otherwise known as sigma squared, I like to put a subscript x there, is equal to a half. The standard deviation of x then would be equal to the square root of a half. All right, so we've now found the variance. Well, moving on, there's actually a shortcut formula. The shortcut formula just says you can find the expected value of x squared and subtract off the mean. So might as well go do that one as well. So I'm going to continue my table off to the right here. So let's go write out x squared. So x squared is going to be 0, 1 squared is 1, 2 squared is 4. And so what do we expect the value of x squared to be? So this is just another function of a random variable. So let's take x squared times the probability of x. This is going to be 0 times 1/4, which is 0. This would be 1 times 1/4, which is equal to 1/4. And then this is 1 times 1/2, which is a half. This would be 4 times 1/4 equals 1. So if we add this up, the expected value of x squared is equal to 3/2. So the formula that we just saw is that the variance of x can be written as the expected value of x squared minus the mean of x squared. So let's just go try it out. So we just found the expected value of x squared to be 3/2. The mean of x was 1. Got to square that. And what do we get? 1/2. Well, 1/2 is exactly what we found using the definition of variance. So notice those two are exactly the same. All right, finally, there's a very similar formula to the one we had for the expectation of a linear combination of some random variable. This is for the variance of a linear combination. And so it says if you take some linear combination of x, so ax plus b, we ignore the constant, and the a constant comes out in front and is squared. Well, let's go try that out and see what happens. So I'm going to first find the variance of y the hard way. So let's go find y minus the mean of y squared, and then you can multiply this times the probability of y. So let's go write this stuff in. I'm going to move it over a little bit so you can still see the y's over here. So this is going to be 0, and what was the mean of y? Well, the mean of y was 10. How likely does that happen? Well, 1/4 of the time. So if you look at this, this is going to be 10 squared, or minus 10 squared, which is 100, times 1/4 is 25. Let's go do the next one. This is going to be the value y, which is 10, minus the mean, which is also 10, squared, multiplied by how likely that happens. So that goes to 0. Then we have 20 minus 10 squared times 1/4 equals 25 again. The variance should be 50. So this is sigma squared y equal to 50. $50 is the 50 squared dollars is the typical square deviation. Well, according to the formula I had, the variance of y is really just the variance of 10 times x minus 0. We'll just forget the 0. So remember what happens to that 10 when I bring it out? It becomes 100 times the variance of x. So let's see, we have 100. What was the variance of x? The variance of x was 1/2. So times 1/2 is equal to 50. And so the point I'm trying to make with all this is that if you use the definition of variance, you get exactly the same answer as if you use this formula for the linear combination. So the linear combination formula is, those two formulas are very important for you to know. All right, I have several problems that you should do that will force you to practice all of those the definitions that I just gave you, and I guess I wouldn't say these are definitions, these are more theorems, likewise with the shortcut formula. But you should go apply them to all of these problems that you've had so far. One more thing, I have an extended video for this first one that you can watch if you feel like you need further explanation on this. All right, that's it for basic random variables.